All right, everybody. We're still talking about solubility. We are specifically addressing when things are soluble in water. Water is super polar. What does that look like? What does that look like? So we're going to talk about hydration shells. And this is just how water molecules orient themselves. Or arrange themselves around a solute. So when something is soluble, the particles are interacting in some way. The solvent particles are sort of spreading out to make room for the solute particles. And then they're arranging themselves in a way that mitigates or decreases some things like charge-charge repulsion. The polar parts are going to arrange themselves where the partial positive is going to want to be next to a partial negative because opposite charges attract. All right, so let's take a look at this. All right, so salts, which are also called ionic compounds, when they are soluble in water, they split up into their ions. Now I do note polyatomic ions do not break apart into their elements. They stay as one unit. So I put a couple of examples on here. We've got sodium chloride. This is water soluble. So we put AQ, meaning soluble in water. And it breaks apart into its ions. That one's pretty straightforward. Okay, what does this aqueous mean? This aqueous means in water. And this is where we get these hydration shells. So I'm going to draw sodium, positive, and I'm going to draw chloride, negative, right? Opposite charges. And then I'm going to draw water. Water is bent. It's a little less than 109.5, this bond angle, because of the repulsion of those two lone pairs. Okay, so looking at water, knowing it's polar, which part do you think is negative? And which part do you think is positive? Right? We've got two regions here. Well, where are the electrons? Electrons are negative, right? So this is a partial negative. That's the Greek lowercase letter delta, which just in chemistry is a partial charge. So it's not a full-on -1. And then we have partial positives. Right? So where the hydrogens are in the water molecule are partial positive because they have less than their share of electron density in those covalent bonds. And then because oxygen is like a vacuum for electron density, it's sucking that towards itself, those bonding electrons. And so it has a partial negative. This is the nature, the polar nature of water. Okay, so what does that look like? If opposite charges attract, which side of the water molecule is going to be attracted to the sodium ion? Sodium is positive. Opposite charges attract. So how are you going to draw water molecules around the sodium ion? With the oxygen hanging out by the sodium or the hydrogen? Right. I hope you said the oxygens. Now, it doesn't really matter to me how many you draw. I also am really bad at drawing in 3 dimensions. But this has actually been experimentally determined how many molecules actually orient themselves around specific ions. Okay, what about chloride? Negative charge. Are the oxygens going to be attracted to the negative charge of chloride? Absolutely not. They are going to be repelled, in fact. And so the water molecules are going to orient themselves in a different way because the charge is different. Okay, so these are called hydration shells. If it wasn't water, we could call it solvation shells, like solvent. We're just focused on water. Most of this semester, we're going to be dealing with aqueous solutions. I hope you can't hear that. We have a hood going off. I'm just going to ignore it, even though it's annoying. Okay, so I just want to take a look at some of the other examples. This is from last semester when you did net ionic equations. All right, all potassium salts are soluble. This subscript here tells me that I have 3 potassium ions. This subscript on the phosphate just tells me that is the phosphate polyatomic ion. We're not going to break those apart into their elements. All right, so it's important that you have a chart of polyatomic ions. You know their name, their charges. You know that the polyatomic ions are not going to break down into their elements in water. We would have to do like some electrolysis, right? We'd make a Frankenstein there, attach some leads and everything. But it's important to know polyatomic ions, their formulas, their charges, their names. If you are allowed to have that sheet on your exam, which for my class, only if we are teaching online. We do open book, open note, but when I teach in the testing center, and of course I write those exams differently, you do have to know those. And this is important because when you work in a lab, you might not have the time to look up everything. Some of these things need to be memorized for fluency. Oh, I forgot my 2. So I have 2. That's what that subscript tells me, that I have 2 nitrate ions for every 1 calcium to make 1 calcium nitrate. And it's because of their charges, right? Ionic compounds are neutral. Their charges have to add up to 0. But it's important to understand when the subscript becomes a coefficient and when it does not. When the subscript is part of the polyatomic ion formula, it does not become a subscript. Okay. So that is water-soluble ionic compounds, but what if there are things that are polar but not ionic? Well, they still form a hydration shell, but things like sugars are polar, so they are soluble in water, but they do not split apart into pieces. So really, we just write it like this. If we have, and don't be alarmed at the structure. All right, so this is actually why sugars are so polar, is because they have a bunch of hydroxide or alcohol functional groups. But if we're dissolving it in water, we'd start with a solid. We often write solvents above or below a reaction arrow, just kind of getting you comfortable. And then we're just going to write this aqueous. So it does not break apart. You don't have to know these kinds of structures yet. Even in organic, I don't think you cover a lot of sugars. But this is going to be aqueous. So the difference here is solid sugar particles, like granular table sugar, for example, and then dissolved in water, meaning, well, it's invisible. Once it dissolves in water, we can't really see those individual crystals anymore because the molecules have separated. Now, it will orient themselves, and actually we'll see some hydrogen bonding going on once it's all in the liquid state. But we do not see the particles break apart. Okay, so polar compounds that are not ionic don't split apart into pieces. And we're going to talk about something called the Van Hoff factor, which I call the ion factor. And this is why their ion factor is 1. The ion factor tells you the number of particles. All right, but that's a little bit jumping ahead. Just want to set the stage for that in one of our next videos.